Welcome back to The Explainer. I am absolutely thrilled to dive into today's topic because we're going to take the often overwhelming world of dynamic programming and completely transform it. We're building a masterable visual mind map of reusable patterns together. You don't actually need to memorize hundreds of distinct code solutions to conquer these algorithmic puzzles. You really just need to map out how the data flows. Okay, let's map out our core branches. We'll start with a dynamic programming mindset, explore top-down versus bottom-up approaches, and then navigate some key visual patterns, constant transitions, two-dimensional grids, sequences and intervals, and finally, advanced knapsack problems. Master these branches, and you're basically master dynamic programming. All right, branch number 1, the dynamic programming mindset. Let's establish our core philosophy here. Imagine a classic staircase. You're at the bottom, you want to reach the top, and you can take either one step or two steps at a time. To find all the unique paths to, say, step 4, you might naturally reach for brute force recursion, right? Just breaking it down into the paths to step 3 and step 2. And that works beautifully, until you ask yourself, wait, what happens if we call the recursive function for step 40? Just picture the performance cost as that recursion tree branches out, calculating those exact same steps over and over again. To put that inefficiency into perspective, 1 billion. That is the number of operations you'd end up running for just 30 steps. Because brute force recursion recomputes the same intermediate steps time and time again, the function takes on exponential time complexity. The tree literally explodes with repeated work. It's a nightmare. And this perfectly illustrates our core philosophy. Dynamic programming is simply about storing the intermediate results of overlapping subproblems. That's it. We avoid those billion repeated computations by doing the work exactly once, saving the result, and just instantly reusing it whenever we need it later. It is an absolute game changer for saving massive amounts of time and resources. Moving on to branch 2, top-down versus bottom-up. Now that we have the mindset locked in, let's explore the two main vehicles for actually implementing this in your code. Think of this as a fork in our mind map. On one side, we have memoization. This is our top-down approach. It starts at the very end goal and uses a hash map cache during the recursion to remember what it's already solved. It's essentially just recursion with memory attached. On the flip side, we have tabulation. This is our bottom-up approach. Tabulation starts at the absolute base cases, like step 1 and step 2, and explicitly fills an array step by step using a clean, sequential loop, completely avoiding recursion and those pesky call stack limits. So here's the crucial takeaway. Regardless of whether you choose top-down or bottom-up, your algorithmic steps remain wonderfully constant. Step 1, define your base cases. Where do you start? Step 2, write your transition formula, connecting those steps. And step 3, iterate and store the math as you go. Honestly, if you master these 3 steps, you've got the skeleton for almost every dynamic programming problem out there. Which brings us to branch 3, constant transition patterns. Let's look at fixed dependencies. When you're tackling problems like finding the minimum cost to climb a staircase, or maybe maximizing your loot as a thief without robbing adjacent houses, you're going to notice a defining feature. Your current state depends on a strictly fixed number of previous states. Whether you only need the last 2 stairs or the last 2 houses, the transition formula never changes. And because we only ever need a small, fixed number of past answers, we can drastically optimize our space complexity, bringing it all the way down from big O of n to big O of 1. Seriously, we literally throw the entire array out. Ditch it. Instead of storing a massive table of intermediate results, we just use 2 simple variables that leapfrog over each other through a loop. Doing this makes your code incredibly clean and massively memory efficient. It's such a satisfying optimization. All right, branch 4, navigating two-dimensional grids. Let's take our visual logic and expand it into 2D space. What happens when we leave the 1D staircase behind? Imagine a grid where your only allowed moves are to step to the right or step down. This brilliantly illustrates how data flows visually. Since the rules restrict us to moving only right or down, figuring out the number of unique paths to any specific cell is actually beautifully simple. It's just the sum of the paths from the cell directly above it and the cell directly to its left. You just fill out the table, cell by cell, adding the top and left values together. Whenever you encounter grid problems with obstacles or distinct paths, I want you to lock this visual anchor right into your mind map. You'll spot these by looking for a 2D matrix, restricted movement rules, and clear border base cases, like dropping 1s all along the top row and the left column. From there, you just calculate the inner cells by checking their allowed neighbors. And a quick pro tip, Just like we ditched the array before, you can heavily optimize memory here by storing just a single row at a time, instead of the whole massive grid.
Let's keep building. Branch 5, sequences and intervals.
Watch how our mind map just naturally builds on itself here. Imagine we're comparing two sequences, like the words stone and tower. To find their longest common subsequence, if we put one string on the horizontal axis and one string on the vertical axis, we basically build our very own 2D grid. The logic here is so elegant. As you iterate through, if the characters match, you grab the value from the diagonal cell and add 1. If the characters differ, you simply pull the maximum value from either the cell directly to the left or the cell directly on top. It is literally just a grid pattern disguised as a string problem.
But what if we only have one string and we want to find a palindrome inside it? That's where we use interval DP. The golden rule to remember here is, first matches last, look inside. If the outer characters of your interval match, you add 2 to your total length and simply look at the interval squeezed directly inside them. You're just building your answers from the smallest inside intervals outward.
Finally, branch 6, knapsack and advanced patterns. Let's explore the deepest branches of our mind map, focusing on variable dependencies. Up to this point, our transitions have been constant, but ask yourself this: how do we compute a state when it depends on all previous elements, not just its immediate neighbors? In problems like finding the longest increasing subsequence, we can't just look at the last two numbers. The increasing sequence could branch off absolutely any previous number in the array that happens to be smaller than our current one. The crucial thing to understand here is that we are dealing with a non-constant transition, because we absolutely have to check every single pass candidate to see which one gives us the longest subsequence. We inevitably end up writing nested loops. That immediately pushes our time complexity to big O of n squared. And unlike our earlier optimizations, here, memory optimization is basically impossible. You're completely forced to keep the entire array of previous results in memory.
Now, transitioning over to knapsack-like problems, say trying to split an array into two subsets of equal sums, we get a total paradigm shift. We stop using array indices to represent physical positions in a string or a staircase. Instead, we use the index to represent the actual sum we're trying to build. You create a 1D array of reachable sums, literally turning the index itself into your target capacity.
And I've got a massive pro tip for filling that knapsack array. Loop from right to left. You absolutely must iterate backwards from your target sum down to the current element. Think about it. If you go left to right, you'll accidentally use the exact same number multiple times in a single pass, which completely breaks the rule that each item can only be used once. Honestly, it all boils down to this one idea. You don't need to memorize hundreds of distinct problems to get good at dynamic programming. You just need to master a small set of patterns. Whether it's counting stairs, pathfinding in grids, editing strings, or packing a knapsack, they're all just variations of the exact same visual data flow, mapped out right here across our core branches. So, I'm going to leave you with this final thought to really spark your practice. Are you going to try to painstakingly memorize 100 distinct code solutions, or will you master the branches of this visual mind map to solve them all? I highly recommend using this visual framework to anchor your logic. Look for the patterns we mapped out today and go conquer those algorithmic puzzles. Thanks for joining me on this explainer.